Good morning. I'm Dr. Amina Priyadarshini, Professor of PC Department, Rohini College of Engineering and Technology. Today's class, we shall discuss about the interference analysis in satellite communication system. So the interference means the some unwanted effects that will be mixed with our original communication. So when a satellite and the station is in establish a communication, and the signal from some other satellites or some other system may get interfered with the original system, so that is considered to be the interference. So the effects of interference is analyzed here. The amount of interference reaching the detector will depend on the amount of frequency overlap between the interfering spectrum and the wanted channel passband. So consider this figure. So this figure is the power spectral density curve for a wideband interfering signal and a multiple interfering carrier. So first figure indicates the wideband interfering signal. So there are interfering signal whose bandwidth is wide, and another one signal is the wanted carrier signal, which is whose passband lies within this interfering signal. So the next case is the wanted passband, which has a particular band of frequencies, and in which the within the passband it consists of multiple number of interfering carrier signals. So here we are considering two situations. The effects are get analyzed. That first and figure the first figure, a partial overlap of the interfering signal spectra with the wanted passband is shown, and here the fractional interference is given as the ratio of shaded area to the total area under the interference spectrum curve. This is denoted by the symbol Q, and in dB it is denoted by the Q in square brackets. So where the partial overlaps occur, the Q value will be less than unity. So we can say that the Q value should be less than 0 dB. And where the interfering spectrum coincides with the wanted passband, then the value of Q will be equal to 0. So the evaluation of Q will be carried out by the system or the computer used within the system. The second situation here considered is the consider second figure in that within the allowed passband multiple interference carriers are present. So here because of this the Q represents the sum of the interfering carrier powers within the passband. So since it has multiple interference signals, the Q will be the sum of the powers of the interfering carrier signals. Therefore, the value of Q that will be greater than 0 dB. So the Q values are computed for a wide range of interfering and the wanted carrier combinations by the processor itself. So next is the carrier to interference ratio and signal to interference ratio. So consider the antenna or consider a satellite system which the receiving end. So the receiving end there is an antenna which will receive the signal, and it is given through the receiver bandpass section. So first the received signal which has some interference effects. So there is carrier to interference, that is carrier to interference calculated at the antenna level itself. So it is given as C by I antenna. Then signal is passed to the bandpass section. So then bandpass section the bandpass filter is used and the unwanted signals are removed, and it is made to transmit through the passband. So the passband signal also consists of some amount of interference. So that is represented as C by I, carrier to interference ratio in passband. So PB. So C by I and represents the C by I carrier to interference ratio at the antenna level, and C by I PB, which indicates the carrier to interference ratio of the passband level. Next, the signal is given to the detector. So the detector, the demodulation, decoding operations are taken place, and the signal is get equalized, and finally the output is obtained. So the output signal will be the signal to interference ratio. Signal has the signal to interference ratio. So thus the original signal can be recovered. So the effects of the interference is analyzed in these various stages. So here the passband carrier to interference ratio is calculated as carrier to interference ratio in passband, which is equal to carrier to interference ratio in the antenna minus the Q value. So the positions of these ratios in the receiver are illustrated in the above figure. So where it will be seen that both the carrier to interference and the antenna and the carrier to interference the passband are pre-prediction ratios, so which are measured in the frequency range of radio frequency or the intermediate frequency. And also interference can also be measured in terms of post-detector output. So next is a receiver transfer characteristic. So in some situation, a measure of interference in the post direction baseband rather than the IF as well as RF passband is required. So the baseband interference is measured in terms of baseband signal to interference ratio. It is given as S by I. So to relate the signal to interference ratio and the carrier to interference ratio of antenna, a receiver transfer characteristics is introduced. So it is introduced in the on account of the modulation characteristics of the wanted signal as well as the interference signals and the carrier frequency separation. So we can say that the receiver transfer characteristics is abbreviated as RTC. Then the relationship between the signal to interference ratio, the antenna's carrier to interference ratio, and RTC both are related as signal to interference ratio is the sum of carrier to interference ratio at the antenna plus the receiver transfer characteristics. Next, interference levels are considered. So consider a two network of satellite communication system. So first one is the satellite is near S and E, and second network represents as S dash and E dash. So the communication is established between these satellites. So for the satellite S and at E, in this network, the signal from the neighboring satellite as well as neighboring earth station will be considered as the interference. Likewise, for S dash and E dash combination, the signal from the S and E network is considered as the interference. So here the signal from the satellite of S dash to the earth station is represented as interference signal that is known as B1 mode, and the earth station of the S dash E dash combination signal to the satellite is known as B2 mode of operation. So here the interference levels are represented as further follows. So there are two networks R and R dash. So method will describe the R dash interfering with the operation of R. So R, which consists of SE combination, and R dash consists of S dash E dash combination. So satellite can interfere with the earth station E. This begins at a B1 mode of interference, and the earth station can interfere with satellite S, then beginning the B2 mode. So note that the network need not be physically adjacent to each other. They are far away from the place. So when a new satellite network is at planning, then the certain calculations have to be made to ensure that the interference level remains within the acceptable limits. So these calculations includes the determination of interference level that caused by new system and that will receive the interference from the neighboring system. So all these parameters are considered before designing a satellite system and to be planning a satellite system to be launched. So if we consider all these things, then we have to consider that interference should be in limited or acceptable range, so by which a successful communication can be established. Thank you.